All right, thank you very much, Mark. Thanks to the organizers for putting this thing on. It's wonderful to see so many old friends again and make some new ones. So I'm going to try to tell a somewhat coherent story that involves the words in the title and eventually gets to the stuff over there, but I've put it on the right for a reason. We're going to start over here with some things which are hopefully familiar. So, since this is a conference on thermodynamic formalism, I hope it will not shock anyone too much when I begin by considering a continuous map on a compact metric space and proclaiming that we have a variational principle. So this, of course, tells us that the topological entropy, which from now on I'm just going to write as H because I get lazy and don't feel like writing lots of extra symbols, but this is the supremum of the measure theoretic entropies taken overall invariant Borel probability measures. And then we are interested in measures of maximal entropy which attain this, and of course we may also be interested in equilibrium states associated to various potential functions and so on and so forth. Now that's a very general setting, and in order to say much that's specific, we need some more restrictive conditions. So if we take a finite set A and consider the set of all infinite sequences equipped with the shift map, then there is a unique measure of maximal entropy. Which is the Bernoulli measure giving equal weight to every symbol. And in some sense, the game is to see how much of this picture we can recreate in broader settings, and eventually I want to explain those pictures over there and formulate some theorems, and we'll get to it. But in order to do it, I want to start by pointing out 4 properties that the unique measure of maximal entropy for the full shift has. So one is not so much a property, perhaps, as a picture, which is that if you consider the one parameter family of Bernoulli measures, now this is just in the case when you have a 2-element alphabet, then the entropy has this kind of shape. So the maximal value is the topological entropy of the shift. The maximum is achieved at 1/2. And there's interesting questions to be asked about this picture already. So for example, I'm letting myself go into digressions and I'm not even 4 minutes in. Well, I'll try to do better later. Suppose you fix some threshold, which is delta below the topological entropy, and you have some Bernoulli measure, which is in this part. So it has measure theoretic entropy within delta of maximal. And you can make the observation that the parameter of that Bernoulli measure must be within constant times square root delta of 1/2. And this is just because it's a quadratic maximum and it's a basic calculus exercise. And this, generalizing this to a statement that holds true not just for Bernoulli measures, but for an arbitrary invariant measure, leads to a very interesting set of questions about effective uniqueness. So you ask, if you have some invariant measure whose entropy is within delta of the maximum, how close is it to the MME in various senses? And it turns out that it's close in sense of weak star. It's in fact also close in the sense of D bar, and there's a lot of interesting things you can say there. But I'm going to mostly stick to focusing on the MME itself. And I want to point out 3 further ways of characterizing the unique MME for the full shift. So one of these is the fact that it is equidistributed. So the unique MME for the full shift has this very nice equidistribution property that for every pair of words with the same length, the MME assigns them the same weight. More precisely, I should say that each word determines a cylinder, which is a subset of the shift space, and those cylinders are given the same weight by the MME. I'm going to very often just talk about the weight that the MME gives to words because it's quicker to say. So this is one property that the MME has. Another one is that the I'm going to go bottom to top here for some reason, which, well, things are independent. So if I take two words, doesn't matter what their lengths are, then because I'm dealing with a Bernoulli measure, the measure of the concatenated word is the product of the measures of the original words. Oh, that was the property I wanted on top. Oh well. And the final one is a scaling property. The scaling property is that if I take any symbol, any words, then the measure of this word is e to the minus h times the measure of the word w itself. And same thing happens if you put a symbol after a word. Now, the way that I've written these for the example that I'm talking about looks kind of contrived and perhaps ridiculous, but it's in this way for a very specific reason, which will hopefully become apparent a little later on. So what I want to do is to take these three properties of the equidistributed Bernoulli measure and explore how these ideas generalize to a broader class of systems and eventually to the things over there. So, yeah, that's that one. You'll notice that I started by saying let's do compact and continuous, and then I specialized further to symbolic. In the title of this thing, I said we're going to get away from compactness and continuity. So to that end, let me actually state the theorems that we're going to eventually get to, and then try to give some description of how we get from one to the other. I was supposed to show you that list of names after I put the theorem up. Oh well. So here's the first theorem. Consider a Riemannian manifold M, which is supposed to be complete. And before I finish the sentence, I have reminded myself by writing here that this part is joint work with Dan Thompson and Tianyu Wang. Omri began this morning by showing us a preprint, which was 10 years in the making, a little over 10 years, I think. Omri, we beat you by just a little bit. We started this project in July of 2016, and it went on archive last week. So, in fact, both of these you can find on archive if you really want to get into any grisly details beyond what I'm going to say up here. So what's the setting? We have a complete Riemannian manifold with negative sectional curvatures. So at every point, all the curvatures are strictly negative. I am not assuming that they are bounded away from zero. That will be a point of emphasis later on. And I want to assume that suppose that the geodesic flow associated to this is topologically mixing on the non-wandering set. So NW means the non-wandering set inside the unit tangent bundle. We're making an assumption of topological mixing. This is not especially restrictive. No. No. Then we have the following statement. Say that, yes. For every set A inside a certain collection of reference sets, which I will tell you, I won't write it, the collection of reference sets is the collection of subsets of the unit tangent bundle, which is compact and has non-empty interior. So it's a pretty broad class of reference sets. We have the following. The topological entropy of the geodesic flow is equal to, and I'm going to write a couple things here which are not well defined yet, and I promise that I will explain them in due course. So there's a couple quantities here, both of which are equal to the supremum over the measure theoretic entropies, and both of which are equal to the supremum over the compact invariant subsets of measure theoretic, of the topological entropies in the classical normal sense. Moreover, if the geodesic flow is strongly positive recurrent in a sense which I will define eventually, and has finite topological entropy, then there exists a unique measure of maximal entropy. Now let me perform the exercise of going through and highlighting the things which eventually need to be explained. So I'll get that, but I will need to explain what is meant by that. I will need to explain what is meant by topological entropy in this setting because it's not a compact space, and so the normal definition doesn't work. I need to explain what topological entropy with respect to A means, and I will need to explain what strong positive recurrence is. So, before going any further, I should point out that this is by no means something which is new in the sense of a new setting. Many, many people have studied the thermodynamic formalism for geodesic flow in negative curvature in a non-compact setting, including the various people here. I am not going to attempt to link individual names to specific results because I will probably get it wrong, and that would be a talk in and of itself. Also, Dan wrote that section of the paper, so I'm going to make him answer questions about it. The point is that there is a large body of work in settings like this. The main difference that I want to point out is that these works predominantly use Patterson-Sullivan machinery. You build measures on the boundary at infinity. And in the approach that I'm going to describe to this question uses the machinery of specification and expansivity. Also, most of these require a pinched curvature assumption so that the curvature is bounded away from zero and bounded away from negative infinity. We don't require either of those. It can get arbitrarily close to zero. It can become arbitrarily close to negative infinity. There are some results in the cat -1 case, I believe, that are due to Dan and his student Caleb Dulcevar. But even there, I think existence is a question that doesn't get resolved in that paper. Is that right? Yeah. So there's a mouthful of a statement for us. And having done that one first, the second one is much easier to formulate. So if we consider a Sinai billiard, that is a flat torus with a finite number of strictly convex smooth scatters removed, and we consider the billiard map. If the billiard has finite horizon, meaning that the free flight time is bounded, so there's a uniform time such that as your particle moves around the billiard, it's always going to see a collision within a uniformly bounded amount of time. You consider your Sinai billiard map. Then there is a unique measure of maximal entropy. So this is joint work with my recent PhD student, Jason Day. This went up on archive about 2 months ago. And to give this one some historical context, I should point out, actually, before I do the historical context, let me just emphasize how these things fit into the title that I gave this business, which is that here we are allowing things to be non-compact, and here we are allowing things to be discontinuous. So neither of these examples fits cleanly into the framework of the classical thermodynamic formalism, which is why, as part of Theorem A, we have to begin by just formulating and proving the variational principle itself. So, what did I want to say about the history of this one? So by way of historical remarks here, I should mention, of course, Baladi and Diemers. So a few years ago, in 2020, Baladi and Diemers proved this result provided that we consider a table satisfying a certain sparse recurrence condition. I'm not going to give a precise definition of that term. Roughly speaking, it means that you can't have too many collisions that are very close to grazing. So a grazing collision would just fly by a scatterer, touch its edge at a tangent, and not change direction. And something which is close to grazing would make a very small change in direction. And as long as that doesn't happen too often in a certain precise sense, then you have a sparse recurrence condition, and these guys prove that there is a unique MME. They also proved that in this setting, that unique MME is what's called adapted. Now, I know there are a number of people in this room who have done quite a bit of work on hyperbolic systems with singularities and adapted measures associated to them, because when a measure is adapted, then you have the whole Katok-Strelson version of Pessin theory to work with, and you can get very, very strong results. You can build countable state Markov models for it and so on. We have no statement about adaptedness of the measure that we build. But on the other hand, we don't need the sparse recurrence condition. And I will mention in passing that There is a, to my mind, very interesting question to be asked about how big the space of non-adapted measures actually is. So a couple of years ago, Yuri Lima, myself, Mark Diemers, and Hongkun Zhang proved that for certain billiard tables, there do exist non-adapted measures with positive entropy. In a different but related context, a student of mine, Lucas Vaughn, whose name I surely mispronounced, so I should probably write it, he proved that for Markov interval maps, the space of non-adaptive measures is in fact quite big. In the sense that non-adapted measures can take every entropy between 0 and the topological entropy. In fact, they are residual in the d-bar metric in the space of ergodic measures. And so these are some questions which I think would be very interesting to understand in the billiard setting, but that becomes much harder. I did not define it. I do not intend to. We don't work with them. This was just a sidebar to say that different machineries get you different things. Our machinery does not deal with the question of adaptedness, and therefore it doesn't get certain things like countable state symbolic models. Adaptedness means that it doesn't live too much, not too much of its weight is close to the singularities of the map. Singularities of the map, these discontinuities happen at those grazing collisions. I'll say more about that when I go through this result in more detail.
So your result shows that adaptedness has nothing to do with the existence of the
Yeah, adaptedness is not something that is needed in order to get uniqueness of the MME.
And it sounds like theory has two parts. One is the
Yes.
part, one is the MME part. Which is the more important part?
The harder part was the uniqueness of the MME. That was very much the harder aspect of all of that. So I will eventually say something about the outline of how these two results are proved. But for now, since I started off by describing something very simple and then jumped to something not so simple, I had better spend some time, probably the rest of right now, of this hour, or 45 minutes, or whatever it is, describing how we get from one to the other and justifying the title that I gave all of this about keeping things bounded. So, let's go back to this basic framework. And let's suppose we have a mixing SFT. And I'm going to describe a way of producing the Perry measure, the unique MME here, which ultimately leads to the way that we produce the unique MME for the billiard system. And that's the following. If you have a mixing SFT, and I want not to consider a one-sided thing, but a two-sided thing. I also want an eraser. Where have all the erasers gone? Ah, thank you. So, oh, now it's wet. Okay. So, let's consider a two-sided mixing SFT. And consider the following two natural projections from the full two-sided shift to the one-sided forward shift and the one-sided backwards shift. So these are one-sided infinite sequences of symbols from A indexed by non-negative, and non-positive integers respectively. And now, let x plus minus be the images of the two-sided mixing SFT under this map. So I could describe these in a more elementary way, perhaps, as just the set of all forward infinite sequences which satisfy the transition criteria, that's x plus, and the set of all backwards infinite sequences which satisfy the transition criteria, and that's x minus. But these maps are useful to have around later on. And then the topological entropy of the shift space is equal to the Hausdorff dimension of the corresponding one-sided shifts. At least it's equal to the Hausdorff dimension if you choose your metric appropriately. Otherwise, there's a constant scaling factor. This is not immediately obvious, but it can be deduced with a little bit of work. And so if we want to have a measure, it's a candidate for the MME, and one of the things which characterizes MMEs was having nice scaling properties. Hausdorff measures have very nice scaling properties. So let me take m plus minus to be the Hausdorff measures of the appropriate dimension on the corresponding one-sided shift spaces. These satisfy these scaling properties here. That is, if I want to look at the Hausdorff measure associated to a word like this, this cylinder is a scaled down copy of this cylinder. And it is scaled by a constant factor. The metric is just scaled. And similarly, if we go with the other one. So this scaling property is what's informing the way I'm describing this approach. And I would like to suggest that this is another way of thinking of the Perry measure. It's perhaps a more complicated way than you would put in the usual introduction to the Perry measure, but to construct the MME for an SFT, the construction of the Perry measure is to take the transition matrix, take its right and left eigenvalues, and if you build measures out of those, right and left eigenvectors, and if you then build measures out of those in an appropriate way, you're going to get these Hausdorff measures. And now if you put these together, remember the next step in the construction of Perry measure is to take the left and right eigenvectors and then kind of multiply them together in an appropriate way. Well, the way that looks for these Hausdorff measures is we say that we define a measure mu by saying that if you have a word, VAW, so I want to think of this as a two-sided cylinder. So here's the zero symbol. So in the zero position, you have the letter A, and then you have a word V appearing in the negative indices up till there, and then a word W appearing after it. I want to define this to be equal to m minus VA times m plus of AW. So this, I'm defining it as a product, which, is sort of in keeping with this independence idea. So these basic properties of the Bernoulli measure we started with, this idea of scaling, sometimes the word which gets used is that you have a conformal measure, and there are analogs of this for potential functions. So the point is you describe a measure measure on the one-sided shift in terms of its scaling properties. And that's what we accomplish by bringing in Hausdorff measure. This independence, this has to do with the product structure of the measure. And I'll just go ahead and say that this equidistribution is what's going to eventually become the Gibbs property. So I really want to think of these various properties which are going to appear as we work in more and more complicated settings. I want to think of them as representing the extension of certain aspects of the simplest example. Okay. So this is a construction of a measure. Of course, there's a problem, which is that Hausdorff measure could be 0 and it could be infinite, right? The Hausdorff measure at the critical value where it jumps from 0 to infinity, it doesn't have to be finite. So how can you guarantee that this thing is finite? And positive, non-zero. So we need to fill that in. So in order to do that, I will finally say something about all that nonsense I wrote in my abstract about keeping things bounded and various quantities that have ratios and well, whatever it was I wrote. So I didn't define topological entropy because I am expecting that most people know what it is, but let's recall the definition. For a shift space, for now, let me say a one-sided shift space. So suppose I have a one-sided shift space and let me write L for the language. That is the set of all finite words in the alphabet A which represent non-zero, non-empty cylinders. And then, if lambda n is defined to be the number of words of length L, then the topological entropy is its exponential growth rate. And informally, we often think of this as saying that lambda n divided by e to the nh doesn't grow or decay exponentially fast, right? This ratio right here varies slowly, sub-exponentially. For a mixing SFT, one can say rather more. So this will be my equation 1. There are constants. There's a constant q such that, in fact, the number of words of length n is within a multiplicative constant of e to the nh. So not only can this ratio not go to 0 or infinity exponentially fast, it cannot go to 0 or infinity at all. And this is one of the basic facts about proving uniqueness results in thermodynamic formalism. And it's exactly what we need to make the Hausdorff measures behave. So the measure mu is finite and non-zero if those uniform bounds that I've just labeled 1 hold. And they do for a mixing SFT, and you can prove that without too much trouble using the transition matrix, but there's a more flexible proof, which we'll do in a moment. And once you have this, it's now not too hard to prove that it is, in fact, a measure of maximal entropy. And you want to prove uniqueness. And so I realize now that I should have just kept that board down because I want to put 2 other things. So That was uniform bound number one. There are three uniform bounds which play a central role in all of the arguments, and versions of them play a central role in the proofs of both theorems A and B, which is why I'm doing things in this order. So, we have the definition of topological entropy, which is here. We also have the Shannon-McMillan-Bryman theorem. So if I take an ergodic shift invariant measure nu, then for almost every point, the measure theoretic entropy of nu is the limit of negative 1 over n times logarithm of the n cylinder. Logarithm of nu of the cylinder associated to the first n symbols of x. So this is true for almost every point. So this is Shannon-McMillan-Bryman. And in terms of a ratio, I would think of this as saying that the measure of this cylinder, so the measure of a cylinder of length n, is approximately, not n, it's approximately e to the length of the cylinder times the topological entropy. And again, this could go to 0 or infinity at a sub-exponential rate. And it turns out that for this example and other important ones, this ratio is bounded away from 0 and infinity. So it's not true for an arbitrary measure, but it is true for a Gibbs measure. So this is a definition. This is one way of defining Gibbs measure. The name Gibbs gets associated to various measures, and this is just one of them. But if you have a measure for which this happens, then this is a Gibbs measure. So the Gibbs property is a uniform version of Shannon-McMillan-Bryman in some sense. Finally, if you have an ergodic measure, and if we define lambda n nu to be the infimum of the number of words of length n, such that the corresponding cylinders have a union whose measure is at least 1/2, then the Katok entropy formula tells us that the exponential growth rate of this is the measure theoretic entropy. And that's true for every ergodic invariant measure. And again, you can think of this as a certain ratio, the number of words it takes to have an appreciable amount of mass divided by e to the nh, cannot go to e to the nh nu, because this is the measure theoretic entropy. And once again, in the one above it, I should have put h nu there because 2 and 3 are descriptions of measure theoretic entropy. So, hopefully you can guess what the uniform version of this would be. It's that maybe it's true for some measures that you have uniform bounds here. Now the uniform upper bound is, well, let me just say it. Okay, so let me make this a bit of a definition. By item 3 here, I mean that this is what I will call a uniform Katok estimate. And whenever I say those words, what I will mean is that this bound holds for every equilibrium state. Now, not every system is going to have this property. This is something which must be proved for the system or the shift space that you're working with. In fact, I think that if this is, yes?
Exponential plus RH.
Oh, yes. Thank you very much. Yes. And yes. And here I am going to clarify.
So, it's another point for me, or
Yes, so this is the downside of my occasional laziness in notation, is that I do want to be clear that in all three of these, I am interested in measures of maximal entropy. So I am interested in those measures for which the two H's coincide. So when I say a Gibbs measure, I mean one that satisfies this bound. And when I say that the uniform Katok estimate holds, it means that every equilibrium state, my brain is already putting potentials in there. For every MME, you have this bound. So that if a collection of words is big enough that some MME, any MME, gives it weight at least 1/2, then it must be large in the sense of cardinality as well. Yes, so I said equilibrium states because if I were giving the complete story, then there would be a statement for potential functions. Theorem A has a statement for potential functions, for a broad class of potential functions. Theorem B does not. Theorem B is only for MME. And in order to minimize the amount of notation, I am sticking with MME for the discussion. But there is a version for potentials. Keith. Yes. Because if you have one, then you've got the upper bound on this. Yeah, so this is kind of a strengthening of one. Yes. So, at some level, the game is this. The game is to see how these three uniform bounds provide a uniqueness argument, and then to see how we can run that uniqueness argument in the settings of theorems A and B. So let me finish what I was trying to write here about mixing SFTs, which is that this measure mu also satisfies the Gibbs property, and that in fact, one can prove the uniform Katok estimate in this setting. That's a real argument, and I'm not going to get into it. But then there is a sort of classical argument, which goes back to Bowen, at least. Maybe Adler and Weiss should be involved in there too. Which says that if you have item number 2 and item number 3, then mu is the unique MME. Except I wrote 2 plus there. So what do I mean by 2 plus? I mean a strengthening of that Gibbs property to say that there exists some K such that we have a bound like this. So that Gibbs property gives a lower bound, and I want that lower bound not to hold not just for single cylinders, but also for pairs of cylinders. So if you have a pair of words and you want to consider all infinite sequences that see V in a certain position and then see W in a certain other position, then as long as there's enough separation between them, you get this uniform lower estimate. So this is like a second order Gibbs bound. And what the classical argument gives is that together with the uniform Katok estimate is enough to prove that it's the unique MME. So,
You didn't say that U is that.
yeah. Yes, you're absolutely right. I only care about invariant measures right now. Yes. Oh dear, I should have. That was the end of this sentence. Is that this measure is invariant. Very important. Thank you, Francois. Yes, and that comes from the scaling properties that they sort of complement each other. So, I think I've essentially used my allotted time for today, but this is the plan then for the next couple lectures. I want to describe how this framework appears in the setting of theorem A and in the setting of theorem B. In both cases, we have to do some work to just redefine the basic quantities in a way that makes sense when you lose compactness or when you lose continuity. But eventually the story will be that in both cases, it's possible to prove these uniform counting bounds, which is item 1. From those, it's possible to construct a measure which has enough of a Gibbs property and enough of this kind of Gibbs property, together with some kind of uniform Katok estimate that everything runs, and you get these unique MMEs.
Sorry, this is similar to the negative log plus Q.
Okay, thank you. Yeah, my brain switched notation on me mid-equation. It shouldn't do that. So I will leave it there, and we'll pick it up next time. Thank you.